Hello everyone and welcome to the second tutorial of this video series in which we are learning how to use Python to teach mathematics and physics, and in particular today we're going to be looking at how to use the MatPlotLib library to graphically represent functions. So the first thing you obviously have to do is to install this MatPlotLib library, and to do that you have to open a command prompt window, so cmd on your Windows machine. And from here on, we're going to just pip inst matplotlib. Press enter and wait for it to download. Okay, now so once the installation has been completed, you can close this terminal window. We will also need the NumPy library, so we will also install that using the same methodology. Open a command line again, and this time pip install NumPy. In my case, I've already installed it, so it says that requirements are already satisfied, but you'll just have to wait for a while until that has been completed. And then you can open a new instance of a Jupyter notebook. So that'll launch a window in your browser. And now I can navigate to where I last created my tutorial series, and from here on I will explain to you the rest of the details. So we have just finished installing these two libraries, and we are now ready to import them. MatPlotlib plot as plt plot and import NumPy as np. So the first thing we're going to look at is how to plot a set of points. Those points come in a list. So over here I have an example. What you would see here is that I'm referring to the matplot library, right? And then I'm calling the method plot, and I'm passing in two arguments. I'm passing in a first list of points together with a second list of points. Basically, this comes down to the x values and their corresponding y values. So the obvious thing that you have to notice is that there is an equal number of x values and y values. So these are equinumerous sets. That's 2 corresponding with 2, 4 corresponding with 3, 5 with 6, and 3 with 5, as well as last point 2 corresponding with 2. And then I'm also creating a title for that plot, and then I'm calling the show method so to render the graph. Okay, so let's run that and see what it looks like. So that looks pretty good. Alright, so you get this sort of a diamond shape. But what I could do is I could actually separate my list from the arguments inside of the method like such, and then it just gives me the same thing. But I could also do it a bit more sophisticated. I can do it as a tuple in a sense. It's still not the best approach, but it does give me the same result. I'm just showing you all the alternative ways of doing this. So you can come up with your own example of two sets of points. The reason I'm showing you such a basic example is that it's much easier to understand, and this will get quite complicated quite fast. That's complicated to read, so a better way. Okay, let's say you have defined a set of coordinates, and then I'm going to print those coordinates. It comes with pairs. But what I'm going to do is I'm going to use Python to fetch all those and put them in the list as we had the lists above. The plot library only understands the list, but I can start with a set of coordinates and then extract them as lists of first elements and second elements. And this time I'm just still going to call it as x and y in my plot library method. And this time the plot title is coordinate plot with a new line. That's what the \n stands for. And then I change the font size to 20 and change the color to green. So now you get this. Alright, that looks cool. So in this example, I'm going to show you how you can actually go and change the vertices to be dots. Okay, so basically I'm just changing the marker inside of the plot method. I'm specifying that by using the keyword marker. Okay, and then I'm changing that to an O. You can also have caret symbol, and you just change it like a little triangle. You can have a point, that's period, like a full stop. You can have a star. Right, these are the different markers that you can have for your vertices. Okay, I can also change the ticks. That means the values on the x-axis, 2.0, 2.5, 3.0, 3.5, and so on. I can change that to 1, 2, 3, 4, 5, 6. And on the y-axis, I'm changing that to 1, 2, 3, 4, 5, 6, 7. So I'm just illustrating the fact that they don't need to be the same number of ticks. Okay, so here you go, and it looks exactly like expected. But what about the 0? I forgot to include the 0. So if I do that, there you go. Hey, now we have a 0. For the next example, I have to import NumPy because I want to show you that the ticks can also be labeled differently than their actual values. For that, I have this example where we still have 1, 2, 3, 4, 5 for the x ticks, and then for the y ticks we have 1, 2, 3, 4, 5, 6, 7. But this time around, I have a list associated to those tick values with the same number of elements. 1 I'm going to associate with A, 2 is going to be associated with B, 3 with C, 4 with D, and 5 with E, and so on. And then the next line, I'm going to include some LaTeX. That means like formatted Greek text, in this case, alpha, beta, gamma, delta, epsilon, zeta, and eta. And that's what the R is really there for. It stands for raw. You could either take out the R and then put a double backslash, just to escape that backslash. It's going to give you the same result. But let me just go and show you that this is fine. Okay, and I'm going to run that. It gives me, oh, okay, alpha, beta, gamma, delta, epsilon, zeta, and eta. Okay, cool. So I can do quite a lot, eh? If I don't want any ticks at all, I can just pass in the ticks argument and then a blank list and nothing in between the square braces. And for its labels, I just leave that out completely. You could probably do that if you want by adding a label list, which is also blank, and then still doesn't show you any ticks at all. But now I just get this box around it with no ticks or anything. Okay, what else can I do? I can actually also add X labels. That means if I want to label this axis here, I can call plot, the plot library, and then append to that the X label method, and then specify the symbol that I want on that axis. And the same for the Y axis. That means the vertical axis over here, the plot library, and then the Y label method, and pass in the Y label that I want to see on this axis over here. And then I can also tell it where I want it. So I want the X to appear over here to the right, rather than in the middle of the axis. So if I leave out this right location equals right, it's just going to put it in the center. And if I leave out location equals to top, it's just going to put it in the center over here. Okay, and then I can specify the font size of that label, so I get that. Okay, but if I don't like the way that the Y is oriented, I can actually just change that by saying the rotation of that should be equals to 0. That just means it should be standing upright, and now I get that. Okay, so that's pretty cool. Okay, so yeah, that's very nice. Now, how can I actually change the size of the figure? Well, there's many ways I can do that. The first way is to specify the figure size with its X dimension and its Y dimension. Alright, and then it's going to give me a bigger figure overall. But I can also change the default parameters, and I will do that by referring to the plot library and changing the parameters. Then I will tell it that I want my figure.fig size to be 6x4, for example. Okay, but I haven't yet drawn any graph. So if I now want to see how that renders, basically what I'm going to do, I'm just going to go and put an example over here, pretty much the same example as before, but this time it will adjust each and every figure that follows after that line. Okay, so next I have an example where we can look more into the styling of the graph by specifying, for example, the marker. We've looked at the markers very briefly. We chose that the vertices should be little circles. We can provide the line style to be solid. The line width, we can specify that to be any value, really that you would like. In this case, 0.7. We can specify the marker size, so that little circle over here, if we want it to be 5, 10, or whatever the case may be, you can just put in a number. We can also specify the color of the lines to be purple. Okay, and so this is the figure that I get. But there's another way in which to do that. These are shorthand versions of the previous example. Okay, so it just says O. By leaving out marker equals, we can just specify in inverted commas that I want the markers to be circles. LE stands for line style, so instead of typing out line style equals solid, we can just type ls equals dash. LW stands for line width, in this case 0.7. Marker size is ms, and then C for color. And again, I get the same graph. So in the following examples, we will illustrate how to visually amplify your graphs by including a label, such as this one in the top right hand corner. And to do that, we have to include the additional parameter label and associate a name. In my case, I have plotted the vertices with blue dots and the edges with orange lines, which is then indicated by this legend key over here. And I also then have to include a plot.legend method in my cell with the location specified. If I leave out the location, it will just put it wherever it feels like, but I can specify other positions as well. So for example, if I want to have this in the lower left corner, I just have to change that. I can also change the number of columns, which then puts it in 2 columns. So over here in the legend, I've specified n col equals 2. I can also change the border around that legend by turning off the fancy box, because automatically it comes with its border, which is a little light gray with round edges. So I've switched it off by saying fancy box equals false. And then I specify a new edge color to be black, and I call the face color to be white. Okay, here's something really neat we can do. We can actually add text to our plot by specifying to the MatPlot library by calling the text method and then telling it that I wanted 3 units right and 4 units up. I want to write the words, the text string parallelogram. Okay, even though this is more like a diamond, really doesn't matter. And then I want the text color to be red. Alright, so it's going to give me that. So now I can change the position of that text however I want. And I can also add LaTeX into that text over there. So this is LaTeX. This is just going to be the midpoint formula. I have a left bracket and I have a closing right bracket over here. And then I have a fraction and a comma and another fraction. In the first fraction in the numerator, I have x1 plus x2 over 2, and the second fraction is y1 plus y2 over 2. Okay, and that gives me this, and that's why it's quite useful, is because you can now write over your graphs and make it look really cute. If you don't like the way that is and you want to maybe change the text on the graph to be vertically written like that, you can just specify the rotation of your text. Okay, so that's quite powerful, because this concept carries over to not only to the text on the graph, but also to the legends, also to the labels and the ticks and all of those. You can really just specify rotation most of the times, and then it just does what you expect it to do. But if you don't want it to be 90 degrees, for example, you can change it to a 60-degree angle like that. Okay, that looks pretty cool, right? So I'm just showing you all possibilities using kind of similar examples, so that when we progress through this, kind of stay familiar with everything. So if I want, I can also add a little border around the text by specifying bbox, and then as the value for the bbox, I'm going to create a dictionary, and I'm going to give it the face color of white and the edge color of black. Okay, and what that's going to do is basically this. It's quite possible to also add grid lines, as the example illustrates, where I have changed the plot parameters, and then I've set the axis.grid to true. And upon rendering that, I then get a graph which has grid lines in it. Okay, so that's something that I like to keep on while progressing through this tutorial. So for the next example, we will illustrate how to annotate the labels to the vertices. So what you'll see here is that I have introduced a subplot, which just basically means we're going to be drawing 2 graphs on the same set of axes on the same figure. And then I've also assigned the variable x to that subplot. Okay, and so we're going to then scatter those points in the x and y list about the figure. Then we're going to annotate to the axis the first label of the labels list. That means we're going to take A, we're going to place it at position of x0, y0. Okay, and so upon rendering that, this is what we get. But we can also go and do that systematically for each and every value in the labels list. So then we're going to take the second label. Alright, that means we're going to take B and place it at position x1, y1. Okay. We can then go ahead and do that for each and every label in that labels list. But that's probably not the best way of doing it. You might want to loop through that list, and I'm going to illustrate that in a bit. Let's just look at how you can also then go and change the position of that label by moving it, say, 1 unit right and 1 unit up. And the second label, B, I'm going to move it 0.25 units right and 0.25 units down. We've actually translated them. We can also change the orientation of each of those labels by specifying the rotation. So for example, the third, we've changed the rotation of the label D to 45-degree angle. Alright. But yeah, as I've specified, this is probably not the best way of doing it. You'd much rather want to go and loop through this list over here. So here I have a for loop. And so for the integer I, and I just denotes the index of the elements in the labels list. And letter is then just a variable which is each element in this list, and it enumerates through the labels list. And what it does then is that it instructs it to go and annotate to the axis label the letter from that enumerated list at the specified coordinates with index I, and then change each of their font size to 20. And so this is what you get. So you don't necessarily need to go and annotate each to the axis. You can just do that in the loop. Okay, but I can also go and change each of their XY text position to 2 units right and 2 units up. So I'm translating each and every of those labels. I can also go and rotate each and every one of them. But now I no longer have control over a specific label. It has to apply to each and every label in that list. Okay, so you have to be careful. I can also annotate LaTeX rendered formulas, a markup language. So in this case, I'm going to assign sigma and delta to the first 2 labels. So this is going to look really nice, specifically if you want to teach something like geometry and you have these type of symbols that you need. Okay, so we spoke briefly about this subplots, but it actually goes quite a bit more into detail, because we need to be able to draw multiple graphs, for example, and we would want to do that using this subplot method from the MatPlotLib library, and I'm going to illustrate to you how to do that. So previously we spoke about subplots, but we're about to go much deeper into this topic, and for that let me just clear the memory from the kernel by resetting the Jupyter Notebook. Okay, and then we want to import the MatPlotLib library as plot and NumPy as NP. And so to really get started with subplots, it really doesn't require much. We just need to assign the variable axis to the subplot method, and then specify the number of rows and the number of columns. We can also specify the figure size as before. So in this case, 1 by 2, that's 1 row, 2 columns, and 10 by 5 is the figure size. And so upon running that, this is what I get. I get 2 empty axes, and so now I can actually go and draw graphs on either one of these or both of these. And just to give you a bit more details of how this works, I can actually go and have a 2 by 2 grid. That means I'm going to have 4 graphs or 4 axes instead, with the same figure size, 10 by 5. And so I have 1, 2, 3, 4 empty graphs. So once again, we can have different shapes. We can have 3 by 2 grids. That means I have 3 rows of 2 columns of subplots, and I can have 2 by 3. So for example, then I have a 2 by 3, so I have 2 rows of 3 columns of axes. It gets quite interesting because we can manipulate each of these independently. Okay, I can have a 3 by 3, and you get the picture really. I don't have to go into more of that. We can play around with quite a lot of the features. Just for interest sake, let's call the axes. So I'm just calling the axis, and what it's going to give me is return this figure size array. And there's a bit of details there, so you can see that the data type is an object. Alright, let's get started with some of the features. We can add a title, but the problem is that this is just going to be misaligned, because basically it's going to just take the title, since it's associated with the entire plot, with the entire figure basically, and it's just going to put it to the last axis that we've assigned to this axis variable. And instead, to do a nicely centered aligned title, I'm just going to actually create a text. We've already discussed text on our graphs before. We've actually placed the text on top of the graph, but now I'm just going to place it above the graph by specifying that it should be 0.95 units in the vertical direction, so that the title appears at the top. And then I'm going to horizontally align, center that title so that it appears between the 2 axes, you know, like literally in the middle here. Okay, so yeah, that's a neat kind of trick to creating a title that is correctly centered Yeah, as I've specified, it really doesn't matter where you put that. So if you want to put it here at the very bottom, it's just not really appropriate positioning for the title. So let's actually go ahead and draw some graphs. So for my first example, I have to first define a linear space. So basically here I have a interval starting at -2π and ending at 2π, and that is divided into 1,000 points. And basically I just want to create a line on which I can then define my function or functions depending on how many I'm going to need. So I'm going to render that. We can then call x if you want to see what that looks like, and it's just basically an array of values starting at -2π, which is approximately that value, and then it ends at 2π, and there's 1,000 of these values in between. Okay, so next I'm then going to define a subplot. So I'm going to set that to the axis variable, and that's going to be a 2x2 grid. So I'm going to have 4 graphs. So I have axis defined by index 0, 0, and therefore I call it x0, 0, and then I want to plot on top of that the x values which we've defined above, and I want to draw the sine graph. Alright, so I give it the NumPy function .sinex, and so I'm feeding into the argument for sine, I'm feeding the x values here, and it goes and calculates about 1,000 sine values for that plot, and it goes and draws it. So depending on the number of points that you define over here, the graph might render a bit less smooth. So let's say, for example, if I only want 10 points, then I'm only going to get a certain number of x values, and if I draw my graph, it's not going to look as good as you can see, right? Because that's depending on the number of points that you have in your domain, basically. So I like to keep it at high definition, and that makes my graphs look much better. So my second graph is a cos graph, my third graph is a sine 2x graph, my fourth graph is cos of -12x, and so I get these shapes. So that's a nice illustration there, but we're going to really unravel this a lot and go really deep into how we can really draw nice trigger graphs later. So for now it's basically just a friendly introduction. Okay, so for the next example, we're going to do pretty much the same thing, except that I'm going to show you that it's possible to do 2 graphs on the same set of axes. So here I have 1, 2, 3, and 4 sets of axes, but on the first set of axes I have 2 graphs. I have sine x and I have -sine x plus pi over 2, and it's going to give me this. It's going to draw it with a blue line, that's the sine x graph, and then the orange line is -sine x plus pi over 2. Okay, so just to illustrate that, it's possible to do all that. And don't worry if you don't really understand the trigger graphs now, we're going to look into it a little bit later into more detail. Okay, and then this next example over here is to illustrate that I can have different domains, x values, for my different axes. So for my first axis, I have this linear space, right, from -2π to 2π. For the second axis, I have this linear space from -π to pi. And for my third set of axes, I have this linear space from 0 to 2π. And for the third set of axes, I have linear space from -10 to 3. And just to illustrate that graphically, hey, it's exactly as I've explained pictorially, right? So everything is as you'd expect it to be. Okay, so yeah, nothing really intimidating as yet. Alright, okay, so this next example, pretty much the same thing. I'm copying and pasting from my notebook here, but I'm making small changes each time. I just wanted to illustrate here that I can also go and independently set my x labels for each and every sub-axis. But the only difference here is that instead of saying axis and then .x label, I have to now say .set x label. For the y label, I do the same thing. I say axis .set underscore y label instead of just saying y label. Alright, so as before with the single plot, if we only plot one figure on one set of axes, we don't really specify this set over here, because this set here, to plot on a subplot and to really make any changes to our subplot, we normally have to say .set underscore and then whatever we're trying to set. Okay, so for example, if you're going to set the title, which you'll probably see in a couple of minutes from now, we'll have to say set underscore title, and then in the parentheses we would put the appropriate title that we would like to show out on our graph. Okay, so yeah, over here I've set the labels to X and Y, and I've adjusted the position for the X label to be to the right and for the Y label to be to the top. And I've also changed the color just so that it's become obvious, you know, to be able to see the changes that I've actually made here. So I have an X over here, a little Y over there. Alright, so that's great. Okay, I've also rotated the Y to be upright. Okay, cool. So up to now, in our previous example, for each of our axes, we had to independently assign the metadata. For example, we had to assign a linear space to axis 0, we had to assign a linear space to axis 1, etc. As well as for each of the other metadata. So, you know, we had to set the X label for each axis, we had to set the Y label for each axis, etc., etc. And that's quite cumbersome. So a better way to do that is to use a loop. But before we actually get to do that, we have to take this axis array and we have to flatten it. So to do that, we have to call this method .reshape and pass in parameter of -1. Basically what that does is it forces it to be one-dimensional. The array has been reshaped in such a way that we no longer have double indices. Okay, so basically we have here 4 axes, but they're no longer within a 2x2 array. Alright, and so now we can actually go ahead and loop through that. Okay, and so as a first example, basically we're just gonna create a title for each of these graphs based on the index of the axis inside of the array. So basically what I mean by that is that since I have an axis here, which is a 2x2 array, I'm going to plot each of their graphs, which is fine, we're not focused on that. We're going to reshape that axis, and then inside of that axis I'm going to loop through that and set the Y label and X label for each and every of those axes, and I'm going to append to them. Alright, and I'm also going to loop through that axis array, and I'm going to assign the graph title basically like the way matrix entries work, in a way that when you specify the first entry of a matrix, you would refer to it as the first row and the first column. So in a similar way, we're going to get the graph title, graph 0, 0, graph 0, 1. That's the first row and the first column. That's the first row and the second column. And so that's a nice way for us to keep track of different graph titles instead of having to go and think of new graph titles each and every time. Okay, but the reason I'm mentioning this is because it's so much more powerful than only dealing with the graph titles and only dealing with the X and Y labels. We can do so much more. For example, we're going to loop through the functions and domain list for each of our graphs. So instead of having to define the function for the first set of axes and define the domain for the first set of axes and doing the same thing repeatedly for the second and third and fourth set of axes, we can just have a list of functions. So in this case, I have sine x, cos x, exponential x, and exponential negative x. But I also have 4 domains, which I'm just going to place above this cell, and then we're going to put them in this domain list as well. And then we're going to loop for each axis in our flattened axis array. We're going to assign the X label and the Y label, but we're also going to enumerate through the axis, and we're going to plot each domain together with their function, and then we're going to add to the counter, which was initially set to 0. So it's going to refer to the first element in the functions array or a list, and it's going to refer to the first elements in the domains list, and then it's going to go on to the second one and do the same thing. Alright, so it's just going to do this. This is the sine function over the domain from -6 to 6. This is the cos function from the domain -3 to 3, and it has done that by looping through this list and that list simultaneously in parallel. So it's taking exponential function together with x1, 0, which is this linear space, and then the last one, exponential negative x, together with this domain or linear space, x1, 1, which is that one over there. Okay, and so you get this shape over here. And also I've maintained the graph titles in the format that I've preferred it before. But yeah, we can also put our domains down into the list. We don't have to put them up there separated, and it's automatically gonna do the same thing, you know. It doesn't have to be outside of the cell. Alright, so that's really nothing new. I've just copied and pasted, but I've changed it a little bit. This is quite a powerful thing to be able to do. We can also have our names, instead of having graph 0, 1, 1, 0, and so on, we can just assign names in a list as well. And then instead of just looping through the functions and the domains list, we can loop through all three of these functions, domains, and names. And then it's just going to give us an appropriate title which is associated to that specific curve. Alright, so that's pretty cool. So in the next example, I would like to have a bigger grid just to illustrate to you that it does not have to be a 2x2 figure. It can be a 2x3 figure, but then obviously your list has to have 6 functions, 6 domains associated to that functions in the correct order, and 6 names or graph titles for each of those functions in the appropriate order as well. But the methodology pretty much remains the same. The only difference is that we have more graphs. But this is pretty cool because I can also set the X ticks and the X labels for each and every graph. So what I mean by that is, for this example, I've chosen that for the first graph and the second graph, I want to have ticks. Okay, but I've chosen to relabel my ticks 1, 2, 3. I wanted to change that to ABC. For my second graph, -4, -3, -2, 0, 1, and 2, I want to keep that in the same way, and so on and so forth. Alright. In this section, we're just briefly going to look at an alternative way of plotting an axis grid. And the reason for doing this is because in certain circumstances, you might not want a rectangular or a square grid layout where each of the axes take up a specific position. In this graph, you might want the set of axes, a particular set of axes, to take up a specific number of columns or a specific number of rows. And to be able to do that, we need to take this approach, which is a little bit more flexible. As an example, let's look at this piece of code where I have a 3x2 and a 2x2 set of axes. In the 3x2 grid of axes, I have 3 sets of axes taking up that entire space, but the 2x2 axis is reserved for graphs with position 2 and 4 taking up that entire space. So we have this unconventional sort of layout. And on this section, I'm not going to go into much more detail. It's just enabling you to become more flexible in your presentation and so on. The rest of the methods that we've employed in the previous section is still valid here. The only real difference is that we have to refer to the library method add_subplot, and then also specify the grid dimensions and the graph axis positions. For this next section, we're going to look at overlapping graphs, and in particular that means graphs on top of graphs. So we're going to have like a small graph on top of a bigger graph, and to do that I have this piece of code. I've defined these two curves, y and z. Y is just the x values from this linear space squared, and z is just the square root of those values, where I instantiate a figure and then I append to that axis by calling the add_axis method with some parameters inside. And then I have a second set of axes which I'll call my new axis. So I have my main axis and I have my new axis, and the dimensions are basically passed into the set of axes as parameters. That is the main set of axis positioning parameters from left and bottom, as well as its width and height. And then the second set of axes, which is on top of that set of axes, we have the same parameters, left, bottom, width and height. And then obviously those numbers have to be significantly smaller, compensate for the fact that we want a graph on top of another graph. But we can adjust the left and bottom parameters so that it appears in a position that we're comfortable with or that we prefer. We now have moved this smaller set of axes 0.25 units from left, from this vertical y-axis, and we've also translated the second set of axes by 0.3 units up. Okay, you can play around with those parameters, and we can still use all of the previous features for the subplot method in this specific methodology to plot our graphs. So we can have titles to our graphs, we can have titles to each axis, we can have the label in different markup languages, we can move the x labels to the far right and the y labels to the top. We can change the color of the graphs by just specifying as before. On top of the axis, we can call the set_ method for the x, y labels and the title, as well as the ticks. So that's pretty cool. So up to now we've looked only at the axes and the grids, but we haven't really gotten into the details of each function, and we're going to start by doing that right now, and that's what this section is reserved for, is to dive deeper into the curve types and how we can manipulate those and so on. So I'm just going to reset the kernel. I'm going to import the MatPlotLib library and the NumPy library, and we're going to start looking at linear functions, and we all know that a linear function is basically defined by its parameters m and c. So I've specified those over there, and I've also specified a domain of x values as a linear space between the endpoints -3 and 3 of 100 points. And there's many ways in which you can define a function, but I've just done that using the define keyword here, and what that does is it will return the value m multiplied by a particular value x from the domain, and then it's going to add c, the constant 2, to it for 100 different points. Okay, so we can see what that looks like by going printing f of dx, and it just gives us this list of values. But we now want to plot this list of values, and to do that, basically the same as before, instantiate a figure, and then we call the plot method, and we pass in the domain of our function together with the function itself, and it just gives us this straight line. Alright, so that's very easy. But what I don't really like often is this box around it, and previously I've shown you how we can actually move the axes so that it's centered in the way that we want it. It's centered through the origin. Okay, and to do that, basically you just have to adjust the spines of your x variable, which is a subplot of that figure. Then we can set the y ticks and the x ticks and the color and all that other stuff. Okay, so we get this, which is a much more appealing graph, especially for like textbooks and tests, stuff that educators and lecturers and even book writers, data scientists, and these people have to be able to do. Okay, so that's why I find it quite important. So what's going on here actually is that we've set the left spine to position 0 and the bottom spine to position 0 as well, and then we've just actually removed the color for the right and the top. Okay, so if you remove these two lines, you're gonna see that I still get this little box, but it's only the top and the right. So I've actually removed the color, but there is yet another way of doing that. We can just set all the axes spines to 0. Okay, then you don't have to worry about the color, you just have that piece of code. But you can go and set the default parameters, and I think that should apply to all your graphs. That's a happy ending. So we want to, for example, be able to set the ticks irrespective of these numbers. Perhaps you want to have only ticks at -3, -1, 1, 3. Those are the odd numbers on the x-axis, and this is what it's going to give me. It's going to give me -3, -1, 1, and 3. And on the y-axis I might want to skip 2, just for example. So that's not something that you're unfamiliar with, it's just that we're repeating a lot here. Alright, okay, next we're going to look at the parabola in turning point form. Alright, the parabola is basically the function defined by parameter a times x minus p plus q, and we can go and define that in Python like previously. We've defined a domain of x values between -3 and 3, 100 points, and then we've defined the function f of x by returning exactly that expression. We can go and look at that if you wish. We're gonna have to define the value of a. So here's an example of that. Let's say a is 1 and p is -1 and q 1. Okay, so just 1. And then we want to look at what is the values of x of f under that parameter assignment. And then we can go and plot this, which is actually quite easy. All you really have to do is to instantiate a figure object again, add a subplot for the axes and the ticks and all that stuff, and then instantiate the plot method, pass in the domain and the function, and voila, you get this pretty graph. I'm including all the ticks from -3 all the way to 3 on the x-axis, and from -3 to 3 on the y-axis. The only problem is it's not showing all the ticks on the y-axis that I want, because our function is really only restricted from 0 upwards in this specific example. But to change that, you can set the y limit on your axis by typing ax set _y lim, and then you can pass in maybe -2 up to 3, and that should do the trick. Okay, and now it's actually adjusted it from -3 up to 3. Next we have an example of a parabola in standard form. That means the expression of ax squared plus bx plus c, where a, b, and c are parameters. And this time I'm not really going to look at the domain again. I'm just going to give you an example of a nice graph. But first we have to define our function and our linear space, because I do provide them over here in my next cell. So I'm specifying that a is 1, b is 2, and c is 1. Then I instantiate a figure, I add a subplot, and then I change the spine so that it passes through the origins. Okay, I set the ticks and I plot those ticks as well. Once again, a very beautiful graph. It's just going to look like that. Here's another example of a parabola in standard form. It's just that I have different domain, but I also have different parameters, just to illustrate that it can move around depending on how you define your shape, a, b, and c, and so on. Okay, let's look at exponential functions. These are functions that are quite generally discussed at school level and all that. But I mean, this is standard stuff, so you know, wherever you are, you're gonna have to kind of go and learn this. Then again, I'm instantiating a linear space for my exponential function. I'm defining my exponential function as parameter a times b to the power of x minus p, and then plus q. Okay, and actually over here it's not correctly written. That q should be outside. Okay, cool. So now I have my function definition. I'm just gonna go and show you an example of if I choose parameters a, b, p, and q. I plot the figure, I instantiate the plot, and I pass in parameters, domain, and the function value, and I show the graph. Okay, well, that's pretty. Once again, I left out the axes, so it's gonna give it to me in a box, and it's up to you to really change how that looks. If you wanted, you could have made it look more like this. Once again, this is stuff we spoke about much earlier by moving the position of the spines to, you know, the origins. And so that's not stuff that I really want to concentrate on right now. I just want to show you all the different shapes that we can really draw. Because I mean, Python is a really powerful language, and MatPlotLib is a really powerful library. So you should use this to advantage to constructing pretty stuff. Let's look at an example of a cubic polynomial before we get to the more intense things with discontinuities and stuff. Here's a polynomial with parameters a, b, c, and d, and I want to define my function, but I'm just gonna do all this in the same cell. I define my function, here it is, and I also define my parameters up here. I define my domain, I instantiate the figure, I add a subplot, move the spines to 0, I set the ticks. Okay, all that stuff we discussed previously, it was just to emphasize the grid lines and change the figure size to 2 by 2, and then I plot the graph, and that's it. That's the end of the story. And hence I get this beautiful cubic curve. Okay, we have now come to a point where we would like to draw hyperbolas. The problem with that is that they may have discontinuities, and that makes it a bit difficult to draw the information because of the restrictions on the domain that needs to be taken into consideration. To illustrate the problem that we have when it comes to hyperbolas, here I have declared a linear space for our domain, and then I've also just defined the function, which is an analytic expression of a hyperbola. And now I want to declare my parameters p, q, and k, and then also instantiate the figure and the plot method, and then show you what actually happens is that we get a runtime warning where Python responds by saying that divide by 0 was encountered. That means that amongst some of these points in the domain, at the asymptotic value 2, there was a violation of some of the laws of dividing by 0. There is an easy way around this problem. So the approach that we're going to be following is to split our interval into 2 over the vertical asymptote, and then only plot our branches for the hyperbola over those independent intervals. But in order for us to be able to do that, we first need to import the ceiling and the floor function from the math library. And so as the next piece of code will illustrate, here I have parameters p, q, and k, which is associated to our function definition. we have the x size and the y size, which is basically just the distance that I'd like to cover my graph inside of the axes. Then I have the vertical asymptote, which is equals to p. And over here I have my domain, which is split into two intervals. Okay, the first one is ranging from the x size divided by 2, in our case 10 over 2, which is 5. And then I calculate the floor of that, which is going to be still 5, and I append a negative to that, so as to start from the very left of my interval, and then I reciprocate that value, making it into a fraction. Alright, so, and then I add to that the vertical asymptote, and then I want to calculate 100 points between those two interval endpoints, and I do the same to the right of the vertical asymptote from 2 onwards. Alright, so then I define my branches based on those intervals, and then I just plot those branches over those two intervals, and I get this shape. Okay, so that's very cool, because now I no longer get any errors or anything like that. Okay, so we can go a bit further than that, and as in the previous tutorial, we've also set our spines to the origin. So as this example illustrates, I've now just moved my graph spines through the origin at x equals 0 and y equals 0. The problem though is that my x ticks are automatically incremented in units of 2, where I would like it to actually be in units of 1, for example. And to be able to do that, we need to revert back to some of our previous lessons, and where we've defined the create list definition over here, which basically takes two interval endpoints and it generates within units a number of ticks for us to be able to plot in our function. So here I have a new x list and a y list, which we're going to also plot onto our axis. So let me just copy this and paste it in the correct place. So this should actually just be over here under my axes. And so now we get this where all of the units are visible from all the way from -3 all the way to 7. And so you can see clearly that the x size is still 10 and the y size is also 10, since from -3 to 7 that's 10 units. From -2 to 8, that's 10 units. I would also like to be able to do a bit more than that when dealing with hyperbolas. I want to also visually emphasize the horizontal and vertical asymptotes inside of my picture. So I can just go and create an additional plot for each. So L and O represent the vertical asymptote, where R and S represents the horizontal asymptote, and I've plotted O over L over here. And I've also plotted S over R over here to give me these new blue dotted lines over here. And so that makes the graph more, visually appealing. Here's another example of hyperbola, where the parameters P, Q, and K have been adjusted to 0, 0, and -1. But all of the other information is pretty much the same as in the previous example. And all that's really happened is that we get the branches in the second and the fourth quadrants. And so this is what you're going to get. I can also manipulate these parameters, say that I want this to be 2 and -1, then it's going to be translated a couple units left and up, and so it looks like this. We are now equipped with the tools to look at similar shapes, for example non-functions such as circles. For that, let me just reset the kernel and import the appropriate math libraries. Then we're going to be looking at a circle which I've defined over two intervals, from the radius 0 to r, and then from -r to 0. I've divided that up into 100 points, and then I define the function as the square root of r squared minus x squared. Okay, so this is an analytic approach to defining a circle. And then we're going to plot 4 branches of a circle. That means I'm going to plot the first quadrant, second quadrant, fourth and third quadrant independently of each other over these intervals. So I'm going to plot f of x1 over the interval x1, and I'm going to reflect that in the x-axis, and I'm going to plot the branch to the left over the interval x2, and I'm going to reflect that in the x-axis again. So it's going to look like this, and it's going to have 4 different colors for each branch. So that's one way of defining how a circle can be constructed. But there are other ways which we're going to look at later. But this allows us to also define other conic sections. So for example, I want to be able to plot an ellipse, and to do that, all I really have to change here is to introduce the parameters a and b, And so this is the analytic definition of the ellipse. Alright, so it's going to look like that. If I swap A and B around, in other words, if I make B2 and I make A1, then I'm going to get a vertically elongated ellipse like that. So that's cool because, you know, it allows me to do all this analytically. And we can also do something similar for the hyperbola. This is a conic section where I have defined the hyperbola as the square root of x squared minus a squared. Once again, it's just going to be the reflection of these branches over those independent intervals. And I can also do a hyperbola which is defined as x squared plus a squared times by b over a. That's going to give me that shape. So yeah, really nothing here is difficult, but I would just also like to illustrate we can align the axis spines to the origin. And so I get this picture over here. That's really nice. Okay, so this is very helpful, I'm sure, because a lot of people, they always use like rudimentary tools when it comes to constructing visually appealing graphs, and it really takes a lot of time to do that, and also the flaws are quite obvious. So you should really be using the correct tools to construct these nice figures, especially if you're going to print them anywhere. I'll show you how to save them in a bit. There's quite a lot that I still want to talk about, so just hang in there, we're going to get there. So I'll see you in the next one.